I'd like to start off by thanking everyone that is present this afternoon. Quickly note, this is my first scientific workshop, so I may sound a bit nervous at first. My name is Mathieu Gagnon. I'm a recent engineering graduate from l'École de Technologie Supérieure. Today I'll be presenting Arctic analog field tests of rocket plume erosion with Moon and Mars regoliths that were completed with the help of Pascal Lee and the Mars Institute. Next slide, please. Like some of the speakers you heard earlier today, obviously plume-surface interaction is very relevant for us going to the moon. For our project, we're going to be focusing a bit more on the Mars interaction. So the project first began by looking at limited recent Mars plume-surface interaction images available. So first we have the Phoenix lander from 2008 in the bottom left, followed by the InSight lander from 2018 in the top right, and finally the Zhurong lander from 2021 in the bottom right. The main takeaway from these images is that erosion depth appears to be limited in ice-rich regolith, as is the case with the high-latitude Phoenix landing site, where approximately 2 cubic meters of regolith were eroded before exposing subsurface ice. This erosion was much more substantial, as we can see in the images, in depth, where there was ice-free regolith near the surface that had been exposed to the direct exhaust from landing thrusters, as is the case with InSight and Zhurong. So the aim of our test is to better understand plume surface interactions and help reduce landing and launch risk for Artemis, CLPS, and eventually Mars. Next slide, please. These tests were conducted during the HMP 2023 field campaign on Devon Island, which is the largest uninhabited island on Earth. It is also home to the largest expanse of frigid polar desert, which offers a perfect opportunity for analog Moon and Mars field tests. The main reason being that the island features an approximately 20-kilometer wide crater by the name of Haughton crater, which is comparable to Shackleton crater on the lunar south pole of the moon. The specific points of interest for this experiment were the abundance of water ice-rich permafrost, along with an active layer that thaws annually. As a quick aside, the Haughton-Mars Project would like to thank NASA and its private sponsors for their continued support since 1997, allowing for experiments such as this being conducted. Next slide, please. So a little bit of context about my background. Obviously, coming from an engineering background, I have less theoretical scientific knowledge, but a constant interest to learn through hands-on opportunities. This brought me to become the project manager of Rocky TS, which is Canada's most decorated student rocketry team, and gain lots of experience with solid rocket motors. So when Pascal, my co-author, came to me with this project, I knew exactly how we could test it. I began by selecting a sample of three 54 millimeter solid motors from Cesaroni Technologies, increasing in total impulse. Then I designed and built a static test stand, which would allow the motor to fire directly into the surface. The area selected for these tests was Von Braun Planitia, which features glacial-lacustrine surface deposits as a result of glacial meltwater. Here we can see an image of one of the test stands in action for the firing of our FOS motor test that we performed. Next slide, please. The results of these tests were quite conclusive in that each test formed an erosion pit with a max depth ranging from 17 to 28 centimeters, which is well within the 1 meter active layer. An interesting point to note is that tests 1 and 2 form pits with an identical geometry that we can see on the right, featuring a funnel formed by slumping of the granular material caused by exceeding its critical angle of repose, which we can characterize as secondary erosion, which is very similar to what Dr. Metzger pointed out in his erosion rate of lunar soil under a rocket paper. This is then followed by a simple cylinder and ending in a distinct inverted light profile, which has implications I will touch on briefly later. The third test had a slightly different end geometry with an inverted cone profile, possibly caused by the larger outer funnel collapsing inwards a bit more than the first two tests. Next slide, please. Here we have a table presenting our preliminary results featuring the main parameters and measurements for each test. So as we can see, the difference between each of the motor tests comes solely from the burn duration and not average thrust. This ensured that only one parameter was modified while increasing the total impulse for each test. We then looked at pit diameter, depth, total volume excavated, and coarse ejecta range. Next slide, please. The data of all three tests were then plotted in function of excavation volume versus total impulse, and a formula was derived to find the line of best fit between these three tests. This formula introduces a new excavation coefficient for estimating excavation volume of a specific soil area with our static test stand based on total impulse. So for the HMP von Braun planitia, with these three tests, we found a coefficient of approximately 3.5, and we aim to perform more tests to get a better idea of accuracy of these coefficients. Next slide, please. Quickly, I'd like to touch on mapping of the coarse ejected material presented in our results. We achieved this by using a high visibility paint of the coarse material found directly on the surface of the excavation area. We then measured the maximum range at which distal ejecta was found for each of the tests. So as we can see, each test resulted in material being projected further and further from the rocket firing area. Next slide, please. So our initial results show that there appears to be a linear relation between excavation volume and total impulse in similar soils, which can be characterized by the excavation coefficient presented earlier. Furthermore, the inverted light bulb geometry has major implications for pit stability and surface plume dynamics that will also need to be further evaluated to better understand how these may result in possibly mission critical failures in the soil found beneath the landers. Finally, additional field tests with larger motors are needed to continue mapping excavations, along with more tests in terrain with varying ice concentration, as I touched on earlier, with the high and low ice concentration affecting excavation volume. I'll briefly add, if you want to contact either I or Pascal Lee, our emails are found here. And yeah, I will now open the floor for questions briefly before passing the conversation to the next speaker.
Great. Thank you so much for that presentation. You didn't seem nervous at all.
Thank you.
So, and maybe Wesley, you have a more specific question for this. And a reminder to folks to put questions in the chat or in the IO. But so you're looking at these tests that occur in a variety of soil conditions and things like that. Are there, and I had a question and it just sort of went away, but like, what are the key issues that you, especially coming from sort of the more technical to the more scientific side, what are the big things that are, I mean, you sort of mentioned some of this, but that are questioning you right now?
I would say it's obviously we've tested on a small scale with similar soils. I think it would be getting just more information about the ice concentration found on, especially when looking specifically at Mars, because we know it is more present in higher latitudes, as was the case with the Phoenix lander, but lesser known in some of the lower altitudes. And that, from our early findings, may play a big factor in kind of those plume surface interactions. So just, I guess, having more information on that, and then continuing to study those effects with larger and larger thrusters that can simulate those found on landers.
Cool. Great.
Thank
Thank you so much.